Okay, next we consider two examples of limit points. So the first example is given by a set E, which is the set of this 1 over n. N is an integer, is a natural number. So it's like 1, 1/2, 1/3, so on and so forth. So this E is a subset of R, and the question is, what is the limit point? What are the limit points of E? Okay. So in this case, it is very easy to check. So you should check it by yourself. That the limit point, there is only one limit point of E, and that's 0. And one way to show you this is you can easily get a sequence of points from E that they converge to 0. Okay. And notice that this limit point 0, is not a point of E. Okay, so it's outside of E. So this also to verify what we said earlier, at a limit point of a set, it doesn't have to be in the set. Okay, and you can also check there are no other limit points of E. This is the only one, and all the points in E itself are isolated points. The reason is when we draw the line, the number of real lines, the line of real numbers. This is a 0, which is not in E. This is a 1. So 1 is included, 1/2, 1/3, right? And you look at any point. Say I zoom in, maybe somewhere in here. Then this is the n. This is maybe 1 over n minus 1. This is the 1 over n plus 1. So you can see that for every point in E, you can draw a neighborhood of it. You draw an open interval of this point. Say, for example, you look at the point of 1 over n. There is a neighborhood of this 1 point, and that only contains 1 over n, but not any other points from E. Okay, so when n gets larger and larger, you just need to make sure this interval is getting smaller and smaller. It doesn't overlap. It doesn't contain the two neighbor points. But in any case, no matter how large the n is, you can always draw a neighborhood like this. Okay, so that's why all the points are isolated points. Okay, so that's the first example. Second example is, say I have a set E. Again, it's a subset of the real numbers, and is composed of square root m minus square root of n. M and n are natural numbers. Okay, and what I'm trying to claim here is that all the the set of limit points is all the real numbers. That means every real number can be approximated by a sequence of points in E. Okay, so to show this, I will just need to show that every positive real number can be approximated by a sequence of points in E. The reason is, if I can show that, then I just need to reverse this, because this m n can be from any real number. So I can get a negative of this sequence. So if I have a sequence xn convert to x, the negative xn will convert to negative x. Right? So it's okay for so we can prove the case for all the negative real numbers as well. And it's easy to get the case for x equals to 0. So let me show that for x greater than equal to 0. So suppose x is greater than equal to 0. Then let me define the xn in this way. So here, the xn for the given x, I'm going to define my xn as the difference of these two square roots. And notice that this is just the square root of n squared, which is just n. So it's very simple for the second term. The first term, here you have x plus n squared. Note that x is a real number, so x plus n squared is not necessarily a integer. So I take the floor of this integer. So this floor means the largest integer that is less than or equal to this number. So for example, if this number itself is integer, then the floor is just the integer itself. But if this number is, for example, is 2.3, then taking the floor will give you the 2. So only give you the integer part. So the largest, so taking this is the largest integer that is smaller or equal to the argument here. So now I have another integer inside the square root and take a square root of that. And again, this doesn't have to be a integer, right? So the whole thing doesn't have to be integer. But this xn will be from the set E because it is a square root of an integer minus a square root of another integer. So this xn belongs to this set. All right. So now let me show that the xn will converge to x for n tending to infinity. Okay. So to show that, I first try to show that xn is less than x. For every xn, it is less than x. The reason is we know that this is the floor of the integer inside. So that's why this taking the floor is less than or equal to the number itself. Right? So that's why xn should be less than or equal to this number. I should use this. Okay, so that's why this number will be less than or equal to this number. And this number, I didn't change it. So that's why xn should be less than or equal to the difference of these two. Right? And the first term is the square root of a square. So that just gives me x plus n. The second term we said is just n. So it's just the x itself. The n is cancelled. So that's what happens when we check the upper bound of xn. The xn must be less than or equal to x. On the other hand, since this is the floor of this of the argument inside, is this number, so it must be bigger than or equal to this number minus 1. Right? Remember the example we had earlier. If you have 2.3 and take the floor, that would be 2. So 2 must be bigger than 2.3 minus 1, which is 1.3. So this is like that. So it has to be this floor of this number has to be greater than or equal to the number minus 1. And then you take the square root. Okay. So in this case, I have a lower bound for xn. What I'm going to show is that this lower bound is tending to the outer bound. So this lower bound is getting closer and closer to x as n goes to infinity. Okay. So now to show this, let me denote this squared thing, the left-hand side, and I denote this as the right-hand side. And I know that the right-hand side is bigger than or equal to the right-hand side, left-hand side. So I just take the difference of them, and I know it is greater than or equal to 0. I just need to show that it's tending to 0. So the right-hand side minus the left-hand side this is my right-hand side, x. This is my left-hand side. Okay. And now I combine the x and n, x and this n. So have two negatives becomes positive. So x plus n minus this number. Okay, and then I'll apply the conjugate. So the conjugate means, in the class when we say conjugate, it means that if I have two numbers a minus b, then it is equal to a square minus b square divided by a plus b. Okay, assuming a plus b is non-zero. All right. So usually when we deal with x and b are both positive. Okay, so this is the case here. This is like our a. This is like our b. So it is equal to a square minus b square. So the a square of this is x plus n square. The b square, this square is just to cancel out the square root. Have this on the numerator. So the reason why we apply this is easy to see. When you look at the difference here, you have a square root, and then you would start to think, well, these two cannot directly subtract them, but we can take a square of them. Maybe that's at least easier to check their sign or something, or make it simpler. So this is the case here. So when the numerator, we put the square of them and put on the numerator, you can see these two will cancel and you will have 1 left. The denominator will be just this plus this. Okay, so that will be this plus this. All right, so now you can see the numerator is just 1, and denominator when n goes to infinity. And this goes to infinity, and this goes to infinity. So the denominator goes to infinity, and that's why the whole thing goes to 0. And that's how we show that the right-hand side minus left-hand side will tend to 0 as n goes to infinity. That means when n goes to infinity, the gap between the lower bound and upper bound of this xn is tending to 0. So that means xn will convert to x. So this is by squeeze theorem. Okay, so now we show that for every non-negative number, this sequence of xn convert to x. And I said earlier, you can easily get, if x is negative, you can just easily get another sequence. You can call it negative xn, which are also from the set E, and they will converge to x. Okay, so that's why every real number is a limit point of E. So that's the conclusion we have here. Okay, next we'll show a result about the set of limit points. So suppose I have two sets, E1 and E2. We can show that the limit points, the set of limit points of union of E1 and E2 is equal to the set of limit points of E1 take union of the set of limit points of E2. Okay, so now we have two sets. We want to show that they are equal. We said before that the common approach to do this, or strategy to do this, is to show that the set on the left-hand side belongs to the set on the right-hand side, at the same time the set on the right-hand side belongs to the set on the left-hand side. So to show this, let me first show this. Okay, so I want to show the right-hand side is contained in the right-hand side. So it is very easy to show that the E1 prime belongs to the union, the set of limit points of the union. The reason is, so let's see, what is the E1 prime? It is a collection of limit points of E1. So that means if there's a point in E1, then that means, say if x is in E1 prime, that means there's a sequence of points in E1 that converge to x. So this means if x is in E1, that means there exists a sequence we call it xn, and they belong to E1 and they converge to x, right? So now you have a sequence of points from E1 that converge to E, and apparently the sequence is also from the union of E1 and E2, because this E1 is just a subset of E1, the union of E1 and E2. So you have a sequence of points from the union of E1 and E2, and they converge to x, and that means this x is also a limit point of the E1 union E2. Okay, so by this we can show that if x belongs to this, then x must belong to this as well. Okay, and this shows the containing relation between the two. So you can show this, and you can easily show you can easily show this, right? Just the same for the E2. And you have E1 prime belongs to the union, belong to the right hand side, and you have E2 prime belongs to this. So the union of E1 and E2 must belong to this. Okay, so that's the one direction. So let me now show this direction. So what I need to do here is to show that for any x in this, I need to show that x is either in E1 prime or in E2 prime. Okay, so x is in the is a limit point of union of E1. E2 means that there exists a sequence I call xn. So this sequence is from the union of E1 and E2 such that, and they're distinct. So distinct points from E1, E2 such that the xn converge to x. Well, I have a sequence of points that converge to x, and the sequence from the union here. Okay, so that means at least one of them contains infinitely many terms of xn. Right? I have a sequence that converges to x, and the sequence is from this union. So that means at least one of them contains infinitely many terms in the sequence. Otherwise, if both of them only have finite many terms of the sequence, then we cannot really get this quick sequence, right? Because the sequence is always has infinitely many terms. So at least one of E1 and E2 contains infinite many terms of xn. Okay, so say, for example, you have this. What this really means is that there is a subsequence of xn. So E1 or at least one of E1 and E2 contains a subsequence of xn. Okay, so that is at least one of E1 and E2 contains a subsequence of the xn. And I'll say this subsequence is x and j, then we'll have x and j converge to x. Okay? I have subsequence x and j, which belongs to x1, such that x and j goes to x. And now that means x is a limit point of E1, or in other words, x belongs to E1 prime. Okay, so it is either in E1 prime or in E2 prime. That's why it is in the union of E1 prime and E2 prime. So x belongs to the E1 prime or x belongs to the E2 prime. That means x belongs to E1 prime union E2 prime. And now what we showed is for every point in this, we can show that it's also in this. That means this is a subset of that. Okay. The E1 prime, E1 union E2 prime should be a subset of E1 prime, E2 prime. So now we showed two of them. Show that this belongs to the set, and we also showed the reverse direction. And because of this two, we know these two sets are identical. Okay, next we show a very useful result that is an extension of the Weierstrass theorem you learned in analysis. So it is called Bolzano-Weierstrass theorem. So what it says is every bounded infinite set E of Rn. So there are two keywords, that the set E is bounded and infinite means that it contains infinite many points, but they're all in a bounded set. And this E must have at least one limit point. That means you must be able to extract a sequence from E that they converge to somewhere. Okay, the limit point doesn't have to be in E either, but you must be able to extract such a convergent sequence from E. So this is the extension of the Weierstrass theorem you're learning analysis. So what this says is on the set of real set of real numbers, this is the real line I'm drawing here, and suppose you have E, and that is in a bounded set. So let me say it's bounded in here, within a certain range. Doesn't matter how large the bound is, as long as it's bounded. And you have points in here. There are infinitely many points in here. Then you must be able to extract a convergent sequence. So there must be a sequence of points extracted from here that are distinct and they converge to some point. Okay, it could be one of these points, but it could be some other point within this range. Okay, so that is the Weierstrass theorem you learn in calculus, in analysis. So this is here we're just trying to extend this to the n-dimensional case. So the n-dimensional case is super straightforward to do. What you need to do is say, because the E is bounded, right? So E is bounded means that E is contained in a box. Say E is contained in this. Let me just write it out. A1 B1 times A2 B2 all the way to A n Bn. Okay, suppose that my E is from there. So to show this, I'm just drawing it in a 2D case. Because I have the points E, the set E, which is bounded, that means I can always draw a big ball to contain it, right? And this will be A1, B1. This will be A2, B2. But if it's in n-dimensional space, we can do something similar to this, right? Just use a big box to enclose this set E. Okay, so now I know that for at least for one direction, look at the first direction here, or first coordinate. Okay, I'll have a sequence of points because this is in an interval. So we just apply the one-dimensional Weierstrass theorem, which can show that there's a sequence of points that converge, right? So now I know that I have a sequence of points from E such that their first coordinates or their first components of this sequence will converge because they are bounded in this set. Okay, so that means by the Weierstrass theorem, there exists a sequence I call it xn, xk, that belong to E, such that when I look at the first component, I'm going to denote this first component of the sequence by this. So xk is still a point in Rn. So it has n components. So the xk1 means the first component of xk. Okay, and this will form a numerical sequence. So this will be a real number only, and I know that they will belong to AB. So there exists, since they belong to the interval A1 to B1. I know that this sequence belongs to A1, B1, and they converge to, I say, C1 for some C1 in this A1, B1 interval. And now from this, I got a sequence whose first components converge to a value, converge to a point. And then I start to look at the second component of them. Then I can extract a subsequence there exists a subsequence, I call it xkj, and I will look at their second components, and they will belong to A2, B2. Okay? And then also this sequence of numbers will convert to, say, a number C2, which belong to the interval A2, B2. Okay? So I can just focus on this subsequence now. I still call it xk. It doesn't matter, we can just throw away what I threw away, what I discarded. So only keep the subsequence here. And then this subsequence will have the first component converging to C1 because it's subsequence from the original one. And itself is also, the second component will also convert to a C2. Okay, so you can just keep doing this. Every time you only keep you extract the subsequence from the previous sequence you got, and make sure that the components, the kth component the ith component convert to some ci. Okay, for I from 1 to n. Okay. Okay, so in general, I can have I can execute this until I finish the last component. Eventually, I'll show that there exists a subsequence. I still denote by xk, right? Like I did for here, I can remove this j. I just say that this j is the sequence I need, and then I will show that the nth component will belong to a n, b n, and this sequence as a sequence of numbers will convert to Cn, which is some point between An and Bn. Okay, so now I have a sequence xk, and I know that their first components convert to C1, the second component convert to C2, so they will eventually convert to C, which is defined as C1, C2, Cn. Okay, so this is the point, limit point that we're trying to show, that the sequence does have has a limit point. So, but notice that this sequence, we know that it must belong to this box, but it doesn't have to be in E, because E is just a subset of this box. So the point C doesn't have to be in E, but it has to be in this box. Okay, next let's show a theorem to give the sufficient and necessary condition for a continuous function. So the f is a function from Rn to R, and we say the function is continuous if and only if for every t, for every number t, these two sets E1 and E2 are open. So these two sets E1, E2 are given like this. The E1 is the collection of points whose function values are bigger than t, and E2 is the collection of points whose function values are less than t. So the E1 and E2 are also called the super and the sub-level sets, the super-level set and the sub-level set of f at t. Okay, so to show this theorem, let's first recall the definition of continuous functions in analysis. When you study analysis, you know that a function f is called continuous. A function f is a mapping from a metric space X to another metric space Y. We call it continuous if every open set in Y has a inverse image, which we denote by f inverse of V, open in X. So every open set in Y is inverse image is open in X. So this is the definition for f being a continuous function from X to Y. So here we're considering even a special case where this X is just Rn, this Y is just R. So they are both metric spaces. All right. So let's see. To show that these two are equivalent, we just need to show that this left-hand side implies the right-hand side, and that gives us the necessary condition. Tells me that the right hand side is a necessary condition for the left, and also if the right hand side implies the left, and then we say the right hand side is a sufficient condition for the left. Okay, so let's first show this direction. Suppose f is continuous, and then let's look at this interval, the interval from t to positive infinity. This apparently it is an open interval in R. So this is open interval in R. So the pre-image of this should be open interval, should be open set in Rn. So there, the E1 will be open set in Rn, and also because this is the open interval in R, so the inverse image E2 is the open set in Rn. So they're both open in Rn. Okay, so this direction is really trivial to show. Basically just using the definition for continuous functions. On the other direction, suppose we have the right hand side here. Suppose we know that for every t, these two sets are open, and I want to show that the function f is continuous. Okay, so suppose not. If not, then that means f is not continuous at least one point. Let's say the x0, f is not continuous at x0, x0. If it's not continuous at x0, that means there exists some epsilon 0, which is greater than 0, such that there is a sequence, we call xk, that the sequence itself converts to x0, but their function value does not convert to f x0. That means f, let's say without loss of generality, the function value is always less than or equal to this f of x0 minus epsilon 0. Okay. Okay. So now you can see that since f of xk is less than or equal to that, let's say this is number. Let's fix this as a number, and this f of xk will be inside the negative, in the interval from negative infinity to this number closed. Okay, so this is the interval, and my f of xk in this interval. That means that xk is in the inverse image of this interval. Okay, so that's how we show this. All right, but on the other hand, let's say this is the complement of this interval is just the open interval from this point to positive infinity. So this is a complement of this. So because this is a complement of that, the inverse image of this set will be the complement of the inverse image of this set. Okay, that's why this whole thing here, when we take a complement, will be equal to this. But now notice that inside here, I have a inverse image of this type of intervals. It's like a t to positive infinity, okay, or all the function values bigger than or equal to t. But this is said this is just the E1 for t equals to f of x0 minus epsilon 0. So according to the condition in the theorem, this is open, and this is open means that complement is closed. So that means this set is actually a closed set, and it's a closed set, and I have a sequence xk, and they converge to x0. And xk is a sequence in the closed set, and they convert to x0. Just means that x0 belongs to the closed set, right? Because a closed set contains all its limit points. So the x0 will be a point in this set. Okay, so it is a point in this set means that the function value will be inside this interval. So it's a point in the set means that its function value will be inside this interval. That means f of x0 will be inside this interval, means f of x0 will be less than or equal to f of x0 minus epsilon 0. But this cannot be possible, since this number must be smaller than this number. And that is where the contradiction comes from. And because of this, we can show that f is actually continuous at all the points. Okay, now let's recall a result you learned from calculus. Suppose we have a collection of open sets. So the G alpha is open for every index alpha. So remember that this index set I can be finite, could be infinite. It could be countable and can also be uncountable. But as long as all those sets are open, then you take the union, it will be still open. Okay, so in other words, the union of open sets is still open. It doesn't matter how many open sets you have there. Countably many or uncountably many is still open. Okay. The second statement is similar. So you have a bunch of closed sets. And again, this I index set I could be finite, it could be infinite, it could be countable, it could be uncountable. But as long as all those sets are closed, the intersection of them is still closed. So again, it says that intersection of closed sets is always closed. Okay, again, doesn't matter how many sets you have there. Okay, so we can prove just one of them, and the other one will be very easy to show. So let me show, for example, the first one. Okay, so suppose all those G alphas are open, then I want to show that the union is open. Okay, so how to show this? To show that the set here is open, I need to show that every point in the set is an interior point. So now let's say for any x in the union, I want to show that it is an interior point. Now to show this, I need to show that there is a ball centered at x with some radius, such that the entire ball is inside this union, inside this set. Okay, so because x is in the union of this set, so the x must be in at least one of this G alpha. So there exists alpha prime such that x belong to G alpha prime. Well, because G alpha prime is open, we know that every one of them is open. So the G alpha prime is also open. We know there exists some radius such that the ball centered at x with the radius r will be contained inside alpha prime, right? And it's inside alpha prime, it must be inside the union of those G alpha, because G alpha prime is just one of them. And by this, we show that there exists a ball centered at x such that this entire ball is inside the set. Okay, so for any point, we found that there exists a neighborhood open ball centered at x such that it's also in there. So that means it's an interior point of this union, and because our x is arbitrary, we know that every point is an interior point, and that means this set is open. Okay. Okay, so that's how we showed the first statement. The second statement is rather easy. We just need to show that apply the De Morgan's law. So if GR is open, that means for any alpha in I, that means the F alpha complement, if F alpha is closed, if alpha is closed for every alpha, then f alpha complement is open for any alpha. Okay, and according to our first statement, first claim, this means that the union of this alpha f alpha complement, let me remove the parentheses, doesn't have to be there, just the f alpha complement. So this is also open, and this is open means that the complement of this union, and here is where we're going to apply the De Morgan's law, and this is the intersection of f alpha together complement. So this should be open. Okay, and this means that the intersection of this f alpha is closed. Okay, its complement is open, means that its complement is open means that this set itself is closed. Okay, so this is the this theorem says that if you just have open sets, then just feel free to take a union. You still have an open set. If you just have closed set, then you can feel free to take intersection. It doesn't matter how many closed sets you have, the intersection will be still closed. The reverse is not true. So you have a bunch of open sets, you take the intersection of them, it's not necessarily open anymore. Okay, so that is, there are many easy examples you have seen from analysis. So I will not repeat here. You can create several of them by yourself. But in which case we can still we take an intersection of open sets, we can still get open sets. The theorem here says that if I have GK is open for K from 1 to n, that means I only have finite many open sets, then the intersection of them is open. Okay, so although in general I take the intersection of open sets, not necessarily open, but when I take only finite many of them, it will be still open. Similarly, if Fk is closed, again, only have finite many closed sets, then the union of them will be still closed. The proof. So again, we can just show the first one. The second one can be obtained by applying the De Morgan's law. Okay, so to show the first one. So to show the intersection of this finite many open sets is still open, again, I need to show that every point is an interior point. Okay, so for any point x in the intersection, I know that x belongs to GK for all the k from 1 to n. Okay, but since GK is open, we know x is an interior point of GK. So that means I can find some RK greater than 0 such that the ball centered at x with the radius RK should be contained in GK. Okay, so for every k from 1 to n, I can find this RK such that Bx RK, the ball centered at x with the radius RK, is contained in GK. Okay, so now let's take R to be the minimum value of R1 through Rn. The minimum value of those RKs. It's case from 1 to n. And I claim that this is still positive number because every RK is positive, and I have finite many of them. And that shows me that the minimum of them exists and is still positive. Okay, so you can see that this is where the finiteness plays a role. If I have infinite many of them, then I take the minimum. I do not necessarily have a positive number, right? So that's why the infimum, or taking the minimum, which is like an infimum of infinite many numbers, positive numbers, is not necessarily still positive. Okay, but if I have only finite many of them, then it's still positive. Okay, so the R is the smallest radius value there. Then we can see that the BXR should be included in BXRK because R is even smaller than, it's no larger than RK. Right? So it's a smaller ball, same center but with a smaller radius. And this is in GK. And this is true for all the Ks. And that means the BXR is actually included in the intersection of the GKs. Okay, so now what we showed is for every point X, there exists a neighborhood or open ball centered at X with the radius R. And this ball is inside the intersection of those GKs. So that means X is the interior point of the intersection. And since X is arbitrary, so this intersection, this set here, must be open. Okay, since every point is an interior point. Okay, so since X is arbitrary, let me first say that. It's an interior point. The intersection GK. And since X is arbitrary, we know that the intersection of K and GK is open. Okay, so the second, this by now we should prove the first statement. The intersection of finite many open sets is still open, and the second statement is can be obtained by applying the De Morgan's law, like in the previous theorem. So I leave this for you as a practice. Okay, so we said that if you have a infinite many open sets, then taking the union of them does not necessarily give you an open set. So in this case, we give them a special name when we won't have countably many of them. So if you have uncountably many open sets, that's really hard to get anything. But if you have countably many open sets, we can give a special name to the intersection. So suppose we have countably many open sets, and the GK is open for every integer k, then the intersection of them is called a G delta set. Okay, so intersection of countably many open sets is called a G delta set. So first of all, the G delta set is not necessarily open set anymore. Okay, as we said, if you have finite many of them, you can still guarantee it's an open set. But if you have infinite many of them, intersection of open sets, infinite many open sets is not necessarily open anymore. But in this case, we still call it a G delta set. Okay, as long as a set can be written as an intersection of countably many open sets, we call it G delta set. So delta here is like in the multiplication or the intersection. The G is the Euro notation we used for open sets. So G delta is a intersection of countably many open sets. And similarly, if you have Fk is closed for every integer k, then the union of them, which is not necessarily closed anymore, but we gave it a name, is called the F sigma. It's called F sigma set. Means that it is union of countably many closed sets. Okay, again, this closed set, this set is not, the F sigma set is not necessarily closed. Okay, but it's a union of countably many closed sets. The sigma means summation or the union. Okay, now let's show several properties of the definitions or concept we gave earlier. So suppose K is a compact set in the metric space, then K must be closed. Okay, so a compact set must be closed. This is the claim I'm trying to make. So to show that K is closed, we just need to show that the K complement is open. Okay? And to show that it's open, we just need to show that every point of K complement is an interior point of K complement. So let's say that Y is a point from K complement, and let for any x in K, let's denote the delta x to be the half of the distance between x and y. So remember that x is in K, y is in K complement, so the distance between them must be positive. The half of the distance is also positive. Okay? So that for every x, we find this delta K such that it is positive. So now for this x and the delta K, I'm going to form a ball. Okay? Center that x with a radius delta K. And for every point in K, I'm going to get this ball. So apparently this is an open cover for the set K, right? Since I get every point, I get a ball for every point in K, so they all together can cover this entire K. Okay, so because K is compact, that means this open cover must have a finite subcover. So I have these open balls and a finite many of them. Say I have a finite many of them with a finite many centers. I call them x1 through xn. And just using the balls centered at those endpoints, which is the collection of these balls, finite many balls. For each of these xi, I have a ball, right? And this will be a finite. I find this x1 through xn such that this balls will be also covering this K. So this is a finite subcover of K. And that is all due to the compactness of K. All right, so because of this, we know that only have finite many points and finite many balls there. So let's look at the minimum radius of them. So I set my delta to be the minimum of those delta xi's. Remember that each delta xi is positive, so I take the minimum of finite many of them is still positive. So delta is still positive. And now let's look at the ball centered at the y with this delta as the radius. I'll see that this ball does not overlap with any of those balls in this set. Okay, this is the reason. This is because at the beginning when we chose the balls, we chose those balls, we said that if this is a y, this is the x, and this is their distance, I chose my delta x to be the radius of the ball at the center x. I chose the delta x to be half of this. That means my ball, it is at most this. Okay, for every point x, my ball is at most this. And now I have another, I have this delta, and the delta is just minimum of them. So the delta cannot be larger than the ball here. So the delta will be just smaller than this one. So this is the ball, this is say this is x1, and I may have another x2, and this is their distance, and I also draw a ball, but my delta here is chosen as the smallest of the radius there. So this ball will not intersect with any of them because delta is smaller than any of those delta xi's, is smaller than any of those radius. So that's why the by delta will not overlap with bxi delta xi for any I. So it doesn't overlap with any of those balls, finite many balls. And because it doesn't overlap with any of those balls, it will not overlap with the union of those balls. Okay, so it will not take the intersection of the by delta and the union of these balls. It is still empty. Okay, it is still not overlap. And remember that this is a finite subcover of K. So that means K belongs to this. K is a subset of this. And the by delta does not overlap with this set. That means that the by delta will not overlap with K either. Right? It does not overlap with K means that the by delta should be inside the K complement. So that's why the by delta must be in the K complement. And now what we showed is for every point in K complement, there exists a ball centered at this point, such that the entire ball is in the K complement. And that means Y is the interior point of K complement. And then there will be the standard things, because Y is arbitrary, so every point in K complement is an interior point. And that means K complement is open. Okay, next we show that if F is a subset of K, where F is closed and K is complement, then F must be F is closed and K is compact, then F must be compact as well. Okay, so in other words, a closed subset of a compact set is also compact. Okay, to show this, we need to show that any open cover of F has a finite subcover. So let's say F alpha is an open cover of F. And then because this G alphas together cover F, so the G alpha and F complement will cover the entire space, because this covers F, this covers F complement. Okay, remember that F is closed, so F complement is open. So this whole thing, all the sets in here are still open. Okay, so this is open cover of the entire space, and apparently they will also cover K, because K is just some set. Okay, so this is the open cover for the set K, but because K is compact, we know that there exists a finite subcover of K. So that means I can only use finite many of these sets to cover K. Let's say I use the G alpha 1, G alpha 2 up to G alpha n, and F complement to cover the entire K. So I can find this finite subcover of K. And remember that as FC, this covers K, and F is just a subset of K. So this will also cover F. Okay, but F complement doesn't help to cover F, because it only covers everything outside of F. So that means the G alpha here is a finite subcover of F. They will cover F. And up to this point, we showed that for every open cover of F, there exists a finite subcover. Okay, and this means F is compact. Okay, here's an important theorem from Cantor. It says that if you have a sequence of compact non-empty sets, we call them F1, F2, F3, so on and so forth. Each of them is non-empty, and each of them is compact, and they are in a descending order. That means F1 contains F2, contains F3. In other words, the sequence of sets are non-increasing. Then the intersection of them must be non-empty. Okay, so what this says is, if you have this like F1, it is compact, and you have F2 also compact, F3 also compact. You have a sequence of this, and the intersection of them will be still non-empty. Okay, you must still have some point in the intersection of this. Okay, so that's the theorem. Okay, to prove this, suppose the result is not correct, the claim is incorrect. In other words, this intersection is empty. Okay, so if this is empty, what happens is that the complement of this will be the complement of this, which is X. So the complement of this set will be just X. The complement of this by the Morgan's law is just union of the complement of each one. Okay, and this will be equal to X. Okay, now let's say each one of them is compact. And remember that compact sets are also open. So FKC must be open as well. And the union of them will be the entire X. That means this is open cover of X. And this open cover of X, it must be open cover of F1 as well, because F1 is just a subset. So this FKC is an open cover of F1. But because F1 is compact, that means I can find a finite subcover for F1. So this finite subcover, I call it FKI. So that just means originally I have countably many of those FKCs, but I only need finite many of them. So I call this K1, K2 up to KL. Okay, so FK1, FK1 complement, FK2 complement up to FKL complement, they will cover this F1. So this is the finite subcover. And this is finite subcover. As I said, this F1 should belong to the union of them. And that means the complement of this will belong to the complement of this. So the F1 complement will contain the complement of this union. And then again, apply the Morgan's law. This complement of the union becomes the intersection of the complement, but the two complements are cancelled. So that's why this is just the intersection of those sets, FKIs. So now, up to this point, you can see that this intersection of this finite many sets in my sequence belongs to F1 complement. And at the same time, they will also belong to F1 because, remember that F1 is the largest set and the other ones will be just smaller and smaller. So the intersection of them will be still in the F1. So that means this is in F1 complement and also in F1. Then that means this can only be empty set. So that means this can only be an empty set. And this is empty set, then we get a contradiction. Because let's say that we have this FK1 through FKL. Let's say they are in a descending order. Okay, so FK1 is the largest and FKL is the smallest, and intersection of them will be just FKL. Okay, but remember that every one of them is non-empty. So the FKL should be non-empty as well. And that's why the intersection of just the finite many of them cannot be empty. Okay, and this gives us the contradiction. Okay, and this gives us the contradiction. And that tells us that this cannot be empty set. The intersection of this cannot be empty set. Okay, next we show that any closed box in Rn is compact. Okay, so you suppose you have a closed box in n-dimensional Euclidean space, and it has to be compact. So for simplicity, I just show the two-dimensional case, because higher dimensional case is just a straightforward extension of this, and the idea is exactly the same. So to show our theorem, what we're trying to do here is to show that this box is compact in R2. So here is the picture of this. In R2, I have a box. This is A1B1 times A2B2. I want to show that this box must be compact. Okay, to show it is compact, I need to show that every open set cover of it has a finite subcover. And let's prove it by contradiction. If this one is not compact, then that means there exists an infinite open cover. I call it F. So F is a collection of open sets. Alpha A is the index set, alpha is the index. So I have infinite many open sets that they together will cover this box. So that means I have infinite many of those boxes. They will cover the open sets. They will cover this box. And because this set is not compact, that means I can find such a open cover which does not have a finite subcover. Okay, it's not compact means that there exists some open cover that does not have any finite subcover. So it does not have finite subcover, means that this open cover that I have cannot, we cannot use only finite many of them to cover this box, and also means we cannot use finite many of them to cover any of these 4 equal sized box, right? Because if I can use finite many open sets to cover every one of them, then the union of this finite many, these 4 finite covers, which is still finite cover, will be able to cover this. Okay? So if we do not have open finite subcover for that, that means at least one of them cannot have a finite subcover. Okay? So that's let's say that this first one does not have a finite subcover from this family F. Then I call this this is the A11, and this is at the B11. So this is what I have here. This new interval or side of this rectangle is called A11 and B11, and also this side is B1, A21 and the B21. So that's my new notation. This is just the box to denote this area here. Okay, so now you can see that the A1, B1 means the 2 endpoints in the first coordinate. The A2, B2 means the endpoints of the interval in the second coordinate or second axis. And this 1 here means I've done this bisection for once. I partitioned this for once, I got this. Okay, so now, as we said, I have a open cover for this, but it's not finite. I cannot find a finite subcover from that. So then I start from here, from this smaller rectangle. I can repeat the procedure because I have I have infinite open cover for this, which does not have a finite subcover. So I can again partition this to 4 equal pieces, and then at least one of these 4 equal pieces will not have a finite cover either. And then I will denote that by the next rectangle. Okay, and I will be able to repeat this because, as I said, for each step, for each iteration, at least one of the 4 does not have a finite subcover. Okay, so by repeating this, I will get a sequence of rectangles, and they are nested in one another, and their sides are getting closer to 0, right? It's approaching 0 because every time the size is just 1/4 of the previous rectangle. And then I look at the endpoints, and I generate this sequence of rectangles. Their endpoints are A1k, B1k, and A2k, B2k. And remember that these are rectangles that are getting smaller and smaller every time. The size of each interval is halved every time. Okay, and now you can see that the sequence for the first pair of endpoints will converge to a point C1. I call it C1, and this will convert to another point called C2. Right, because this size is halved every time. This size is also halved every time. So as endpoints, they will converge to some point. I call it C1 and C2. So that means I have a sequence of rectangles. Everyone is nested in the previous one, and everyone has the size as 1/4 of the previous one. And the endpoint, the 2 sides are converging to C1 and C2 respectively. And now let's say where the contradiction is. So because they converge to C1, C2, let's say this is C1, C2. Okay, so this point is C1, C2. And because C1, C2 is a point in the rectangle, in the big rectangle, and so it has to be covered by it's covered by this F, right? It's covered, since F is open cover for the entire interval, entire rectangle. So it's covered by F, that means this point C1, C2 must be inside at least one of this G alpha. Let's say that this point is inside G alpha prime, for some alpha prime. And because this C1, C2 is in G alpha prime and G alpha prime is open, so that means I can find a ball centered at C with some radius r, such that the entire ball BCR is inside this G alpha prime. And that is the circle I'm drawing. This is the open ball that is contained in G alpha prime. And this is a fixed size, right? But remember that the rectangle that is converging to the C1, the point C, is getting smaller and smaller. Eventually, their size is approaching to 0. But here I have a fixed size of ball. It has a fixed radius r. So that means that up to some point, when k is large enough, then this rectangle will be completely inside this ball. Okay? And up to this point, you can see that I can just use G alpha prime to cover this rectangle. And that is a contradiction, since we said that we will never find a finite subcover to cover the rectangle we have. But now we show that there is this G alpha prime such that after k large enough, it actually covers the entire rectangle. That is where the contradiction is. And by this, we show that this interval must be compact. Every infinite open cover must have a finite subcover. Okay, the result above gives us a very useful criterion to check if a set is compact or not in Rn. So the claim we are trying to make here is that every bounded closed set in Rn must be compact. Okay, to show this, let's say that if F is bounded and closed, and then because it's bounded, it has to be included in a bigger closed box. So let's say there is this K is a closed box, then that includes this F. So if F is like this, then there must be a K that includes it, since F is compact. Okay, so this is the F, this is the K. Okay, and now remember that K is a closed box, so it must be compact from our previous lemma, and F is closed. So every closed subset of a compact set must be compact. So that means F must be compact as well. Okay, now let's see an example to apply the theorem above. Suppose we have a set F that is closed and bounded in Rn, and the G is an open set, and F is contained in G. Then there must be some positive number delta, such that as long as the magnitude of x is less than delta, or the x is inside the ball centered at 0 with radius delta, the f plus x must be in G. So f plus x means the collection of sets, collection of points y plus x, where y ranges from the f. Okay, so this is usually notation we use to denote the sum of a point and a set. Okay, so to show this, because f is closed and bounded in Rn, from the previous theorem, we know that f is compact. So keep that in mind. And now what we need to show is, because for every y in f, y is also in G, because since f is contained in G. And the G is open means that there exists some ball with the radius delta y, such that the entire ball is inside G. Okay, so for every point y in F, I can find this ball that is in G. Okay, and apparently, if I collect all those balls with just half of the radius, you see the reason why I choose half of the radius, but it doesn't matter because it's still a positive number, it's still greater than 0. So it's still a ball centered at a y. If I collect all the balls, all these balls where y ranges from all the y, the entire set of F. So for every point y in F, I can have this ball, and this will be an open cover of F, right? To cover the entire F. And since F is compact, we know there is a finite subcover for F. So I call this finite subcover as this. So the I is from 1 to k. So I have a y1, y2 up to yk, and their balls are denoted by this. So this finite many balls will also cover F. Okay, now let me choose the delta to be the smallest one of those radius. So I have finite many balls, I extract the radius and choose the minimum of one of them. And this minimum value will be still positive, okay, because only if I find many positive numbers. So delta is still positive. And then let me check for every point x inside this ball. That means the absolute value or the norm of x is less than delta. And for any y in f, I want to show that x plus y is in G. Okay, to show this, let me say that because y is in f, that means and f is covered by these finite manifolds. This is the open cover for f. So that means y is covered by at least one of them, one of those balls. So let's say that it's covered by the yi prime. So I have the yi prime is from 1 to k, and the y is covered by this ball yi prime with the radius corresponding radius. So the y is in this means that the distance between y and the yi prime is less than half of delta yi prime. Okay, and now to show that, and furthermore, we know that this x plus y, I wanted to show this point is in G, right? But now let me check the distance between this point and the y prime. The distance between these two by applying the triangle inequality, because this is bounded by the norm of x plus the norm of y minus I prime. Okay, so I just combine these two. I get the triangle inequality, I get this. And remember the x is from this ball, that means the norm of x is less than delta. And since y is in the ball here, so the distance between y and the yi prime is smaller than delta, half of delta yi prime. And remember that delta is the smallest one of those delta yi's. So it's the smallest one of them. So this must be smaller than this. Okay, and that's why the sum of these two must be smaller than the delta y prime. So what I showed here is that x plus y, for any x in this ball and any y in the set, I can find some y prime such that their distance is less than the delta y prime. And that also means that x plus y is inside the ball centered at yi prime and the delta yi prime. And remember that this ball is in G, okay? Because for every point y, we chose this delta y such that this ball is in G, right here. So this ball is in G. So what I showed here is that for every point x inside this ball and any y, I can show that it is inside the G. Okay, this completes the proof.